Okay, awesome. Yeah, welcome to Spark Summit again. Is everyone having a good time, learning a lot? Spark Summit? Yeah? All right. So today we'll talk about 700 updatable queries per second and using Spark as a real-time web service. We'll explain what that means in just a minute. To introduce myself a little bit, my name is Evan Chan. I've been using Spark since before 1.0. How many folks here have used Spark since before 1.0? Just raise your hand. Oh, actually, that's a fair amount. That's pretty awesome. I remember in those days, like nobody had really heard of Spark, but being a Scala user, I was very excited. This was a distributed framework, a lot of cool stuff happening. I was like telling everyone, let's use it, and people were like, what's this? You know, but just playing around with Spark in those days, using REPL, you could kind of just taste what kind of a huge change that would bring about. And I'm also DataStack's Cassandra MVP. I've used Cassandra since very early days. And created some interesting open source projects. One of them is a Spark job server, which is still, I believe, the leading REST job management system for Spark. It's in widely deployed today. And FileDB I'll talk about today. So Apache Spark. Most people think of using Spark when you need to scale up. Like maybe at a small scale, you're using something really simple. Then you have a lot of data. You think of, OK, I'm going to use Spark. I'm going to run this on a big cluster. And I'm going to run different kinds of jobs on it. And typically, these are a lot of times, they're rich analytics, what I call rich analytics jobs, and not so much like super time critical stuff. You're talking about, for example, building models, machine learning models based on a lot of data. This is very, very popular, like using Spark, right? Or maybe using those models that you built to score or do predictions on your data. Maybe you can maybe you like to run SQL queries, and these take seconds to minutes, kind of thing. Basically, using Spark is a very fast and more flexible kind of Hadoop, right? And maybe you're using Spark streaming, looking into that. But what if we want to use Spark for lower latency use cases? We're talking about, what are we talking about here? Or basically, you can think of what if I want to scale Spark down? I want to run it and run it in scenarios which typically you don't think of, like maybe run it one node, but for cases where it's OK to have less data. What am I talking about? Low latency web queries. For example, you want to power dashboards. You want to have rich interactive dashboards. Maybe you want to let people slice and dice data in different ways. But you really need to have that fast response. So this is talking about well under a second of response time would be acceptable, right? If someone looks at a dashboard, it takes like 4 to 6 seconds, then that's probably too long. For interactive analysis, for kind of real-time stuff. And typically what you might have heard is that Spark, you don't really use it for this kind of scenario. But one of the messages I want to tell you today is that that is actually not true. Spark actually can scale down very well for these use cases. Leave yourself with some, if you approach things with a certain way. Let's look at the typical web query stack. And as hot as Spark is and as hot as big data is, it turns out that this kind of stack is millions of people deploy this all over the world. And this is still, the majority of programming today is still doing this kind of thing. Basically, you have a web client. It talks to an app server. It talks to a database. This is 99% of the programming world. Even though here at Spark Summit, we like to think that what we're doing is the 99%. But it turns out this is still 99%. And maybe, what if we could use Spark to infiltrate some of this 99% of the world out there, right? You have a web client. It talks to something that talks to Spark. What if we could use Spark Stack for this kind of thing? So the first thing that we want to talk about, we talk about Spark for low latency, is that creating a new Spark context, creating a new Spark application is very expensive. Because if you look at all the things that has to be done when you start up a Spark context, it has to start up a UI. So it has to start up an HTTP web server. when you like to debug your jobs, you look at that really nice UI that shows you the DAG and the event flows. That's the Spark UI. And you may or may not notice, but every SparkContext also sparks up a BitTorrent server. What is that BitTorrent server used for? Well, you need to distribute a jar and broadcast it to all the workers. Or you might need to broadcast some files. Well, that uses a BitTorrent file server. Right? And it has to start up all the application processes, whether it's Yarn or Mesos or something else, and then it has to wait for all those executors to fire up. And on a big cluster, this can take a while. This can take several seconds. Right, so the first thing that we want to do is kind of avoid this overhead and use a persistent Spark context for low latency. And the idea is you're going to start it up one time at the beginning of your application. You're going to pay that startup cost. And then all your queries can avoid that cost. And this is a standard pattern that is used for example, the Hive Thrift server that is used in Spark. How many people use the Hive Thrift server? Actually, cool. And another one, you can also do this using something like a Spark job server if you want REST API instead of JDBC. And this works. This is a fairly standard pattern. It's been in use for a long time, and it works fairly well. One thing that this usually means, usually when you do this, you want to use fixed resources. And usually you're starting out with a fixed number of CPUs and memory per node, this kind of thing. And I think that's actually a good thing because when you have fixed resources, you can plan your cluster usage better. You know that I'm dedicating, 40 CPUs for my queries, right? And that gives you a way to plan out your SLAs and kind of resource better. You know that my other jobs are not going to touch these resources, and these resources, I have guaranteed for giving me some kind of query latency. Another thing that you might want to consider is a fair scheduler. How many folks are using the fair scheduler? Cool, a fair number. So just two quick things to point out. The fair scheduler can, even if you have jobs or queries that take up all of your tasks in your context, the fair scheduler can actually still co-schedule multiple jobs at the same time. And the reason is because in fair scheduler, it doesn't have to wait for all the stages of one job to finish before it starts another one, which the default FIFO scheduler does. The fair scheduler is able to co-schedule things. And let's say some parts of a job finish, and can schedule another part of another job to start first. And another thing that it has are scheduler pools, which actually allow you to even subdivide a context up into smaller pieces. Now, one thing to note is that the default FIFO scheduler actually can do concurrency if one job only takes up, let's say one job only takes up one thread. Then it can actually schedule another job to start before the first one finishes. And that's a behavior that I've observed. So it really depends. So it's not that the FIFO does not allow you any concurrency at all. But the fair scheduler is more flexible. So here's the game plan that we're going to follow. We're going to start a persistent Spark context and run it with the fair scheduler mode. We're going to use fast in-memory storage. We're going to maximize the concurrency by trying to minimize the number of partitions that each query runs. This is actually very critical because the more partitions there's a cost to each partition. So you really want to minimize the number of partitions that you have as much as possible if you really care about low latency. And the last point, some of you will probably consider controversial, but this is what I talk about when I mean scaling stuff down. For now, let's focus on hosting the data on one node, and that way we can avoid network shuffles. A little bit about in-memory storage, just really quickly. Is it really faster than files on disk? Well, you can think of with files I get like OS caching, but the key point is that we want consistent performance, right? You want to be able to hit SLAs, and when you have stuff in memory, then you can avoid you can avoid the uncertainty of like other applications using kind of fleshing out the cache and knowing what to keep in a cache. And some of the trade-offs that you want to make for in-memory storage is that you would optimize for less CPU, right? So that I'm willing to pay the cost of having used up a bit more memory and less compression, like that kind of thing. And some of the new stuff coming out, like Arrow, it's going to pointing in this direction as well. So let's talk about storage for a little bit. Let's say that you use Parquet files. Parquet is great. Everyone uses it. When you can select a few columns, it dramatically reduces I/O. This is great. But you still have to scan a lot of files. And when you use Parquet, you organize your files using a fix. Maybe use a directory hierarchy. But this is not the easiest for filtering stuff. Basically, you can select a subtree very easily, right? But it's not very easy to filter down your data like more than that. You can use RDD caching. So RDD caching is very easy. You can just do .cache, right? And you can optionally serialize it because by default it will keep your Java objects that are in memory like just on the heap. But Java objects, as we know, like you use pointers and you have trees, so that this can use up a lot of space. So we serialize it. So the pros are easy, but on the other hand, like you don't get basically every computation is a full table scan over your data, and it goes over every you have to deserialize entire objects, right? So that's not very optimal, and you also cannot update RDDs. DataFrames are a little bit better compared to cached RDDs. I think most of you guys probably noticed cached DataFrames is not the same as caching an RDD. Spark will actually use an efficient internal columnar storage for storing your data. So it's used up a lot less space than a cached RDD would. And it also offers columnar pruning. So this can be much faster. But you still don't get any filtering, and you still can't really update your data. Why are updates important? Well, you guys might have all heard of the structured streaming talk that's coming in 2.0. So one is that for real-time workloads, for streaming workloads especially, you're always appending new data. So you really want a kind of storage where you can query it and you can get new answers that's coming to you all the time, right? And the other reason why it's important is, especially now that you have structured streaming, you're talking about processing event time, right? So when you process stuff by event time, you can have some updates coming now, but you might have some late events coming in. So it becomes more and more important to be able to update your aggregates, and so I think this points to that updates are becoming more and more important in your storage, right? And I think this is probably self-evident, but filtering is also important because there's basically two ways of speeding up or lowering the latency. One is that you can scan data faster. You can scan the same amount of data faster. And the other way is to filter. And really, you want to do both, right? As an aside, you can't really update RDDs. But what you can do is that you can do a union of a new RDD and an old RDD. The problem with this approach, though, is that if you do a lot of updates, you end up with a very big tree, which is not a balanced tree. It's kind of like a one-sided linear tree. And this creates a huge lineage, and that it actually slows the scan down very significantly. So with that, I'm going to introduce my project, PhiloDB. This is a distributed, versioned, and columnar database. I'm not going to go into the version part very much, but if you're interested, you can talk to me afterwards. And what this is that it is like Parquet in that it offers a columnar storage that can scan data of only the columns you're interested in. And so that leads to lower I/O or lower memory bandwidth, if you think about it that way. But the difference, and it offers efficient columnar encoding like Parquet, like dictionary encoding. But the difference is that it is based on the Dynamo Cassandra model, which I'll talk about in a minute. So it allows you to filter down your data to a much smaller amount, which is very important for low latency, and it is updatable. Don't worry, you'll get these slides posted later. But if you're interested, I did write a blog post comparing this solutions to other Cassandra-based storage formats on O'Reilly, so you can have a look. And basically, it offers two storage engines. One is an in-memory storage engine, and another one is based on Apache Cassandra for distribution and cross data center and all the other good stuff that it offers. So we'll spend a little bit of time on this. This is what the data model looks like. You have a concept of partition keys. And if you use something like Cassandra or Bigtable, it's very similar. Basically, partition keys will group data into one node. But partition keys are used for distributing data. So the idea is that you can spread out your data across many nodes using a partition key. And partition key also allows you to do fine-grained filtering. So you can define this on, say, one UID and pick data from only that. Segment keys, you can think of it like, if you think of it as a spreadsheet, segment keys are kind of like the column axis. And a typical use case might be time slicing. We have a lot of time-based data. And you can use segment keys to do a range scan on, say, a certain amount of time. And FileDB offers a primary key-based ingestion and update. So if you rewrite the data using the same primary key, you'll end up with only one copy of that data. And because of the storage model, we can essentially offer arbitrary filtering of partition keys. It is based heavily on Spark. We use Spark as the query engine. So you can use all of the standard SQL statements that Spark supports. Spark doesn't support everything, but all the selects that you're used to query your data, and you get back DataFrames. You can also ingest data using DataFrames. So you can use the Hive syntax for DDLs, create table, insert into this kind of thing. And as a result of that, that means that you can easily connect it using Tableau and tools like that. I'm a foodie, so I like food. And the name comes from phyllo dough, which is used in virtually all baked goods. It just stands for basically layering of data in a distributed way. This slide is unfortunately a little bit old, but the way that you can think of this is, let's say that you have events coming in through a message queue, Kafka, and you're processing it using Spark Streaming. If you're doing this for a persistent storage, you could then use the Cassandra plugin to store events and read them out very quickly using FileDB to do machine learning. And you can use regular Cassandra tables for doing dashboards. But when you use the in-memory module, it is fast enough that you can actually use that for dashboards as well. One user is using this in the following way. So again, you have the Kafka, you have Spark Streaming. But the way they do it is that they would store order events in FileDB, then they read it out to build a machine learning model. And they can keep updating this model, which is very useful for a lot of applications. Then they take another stream of incoming data, and they can do scoring and predictions and classification on this data. And they will store it again in FileDB using a different kind of schema so that they can read it out for dashboards. So that's how one user is using it. So anyway, enough about that. I'm going to go back to implementing the fast SQL server. One dataset that I love using is the New York City taxi dataset. I don't know if you guys have heard of this, but this is basically foiled data from New York City for the last few years. Every time someone rides a taxi, that ends up as one record. It has your start latitude, longitude, the ending latitude, longitude, the time, and this kind of thing. So the way that we're going to model this data in FileDB is that as a partition key, we're going to pick the first two characters of the medallion. The medallion is basically like a UID for the taxi cab itself. And when we take the first two characters, we're basically sharding this about 300 to 600 ways. With that, we can easily pick out data for one particular taxi or a range of them. But we're also using a time slice for the segment key so that we can pick out, you can imagine picking out a bunch of columns, then we can pick out data across taxi cabs for a time slice as well. There's one, how many people have heard of the async APIs in Spark? So it's not, a lot of people haven't, but This is a really neat API. I'm using the Scala version here, but there's also a Java version, I believe. But normally when you do operations like collect and show, everything runs single-threaded in your driver program. But sometimes you don't want that. For example, for low latency, you really want to run this. You want to run things in a parallel way as much as possible. So what collect async does is that it runs the collection from the Spark workers to your host on separate threads. And for Scala, it returns a Scala future. And this is something that we're taking advantage of for doing low latency. In Scala, you can easily sequence your futures. So you can distribute a whole bunch of parallel reads and get back data and distribute part of that collection, which becomes non-trivial when you're talking about low latency. So here are the initial results. We ran a lot of queries concurrently using collect async. And on the first million rows of the New York City taxi data set, and we're getting about 50 queries per second. And when I analyzed the runtime of this, it turns out that almost all of the runtime was actually that the SQL context does the translation from SQL to a logical plan. It all does it in one thread. And so that was pretty much taking all of that time. Oh, sorry, I guess that was the slide. So there's several things we can learn. One is that the startup latency of a task in Spark is actually very low. It's actually in the low milliseconds. So that by itself is not the bottleneck when it comes to low latency. However, because we're talking about like SQL queries, the SQL query actually takes up a lot of time. The other thing that we learned is that when you can do queries and most of them can filter down to one partition, and again, that depends a lot on the data source. So depending on your data source, the FollowDB is smart enough to be able to reduce a lot of queries to a single partition or to minimize partition usage. But if you can minimize the number of partitions you use, then again, you can spread out your queries a lot. So some things that you can learn from the initial one is that one thing we can do is to cache the SQL to logical plan parsing. And I just want to make an important point. We're not talking about caching results. So what we're doing here is we're caching, I'll show you a code in a little bit. We're talking about caching the logical plan. And that means that as your data updates, you can still execute this cached logical plan again and again and get updated results. But you're saving yourself the work of caching, of parsing the SQL itself. And the other thing that we can do is that we can distribute the SQL parsing away from one thread. That's a little bit more tricky. This is what it, let me see. Yeah, so this is what it looks like. I'm sorry, there's not syntax highlighted. But basically, we're using a hash map to cache the SQL string to a data. It says data frame there, but this is not actually the results data frame. This is simply, and Spark also uses the data frame just to contain a logical plan. So this is all that we're doing to cache it. Oh, sorry. So when we do this, we find out we can eliminate most of the overhead of SQL parsing and get to hundreds of queries per second. And so at this point, you're thinking, well, this is not a lot of data. So what we did was that we expanded this to 50 million rows, which is enough for 1 month of data. And we still got 700 queries per second. So at this point, I'll talk about some different stacks that you can do this with. One possibility is that your front-end app can talk to your app, and you can bring in Spark as a library. And so you see Spark as a library. FollowDB is another jar, so you can bring this in. And basically, you can wrap this in one process, and it runs very fast. So this is what I mean by scaling down, is that you can bring everything down to one node, and you can use this to replace an RDBMS stack, right? And so this works for some cases. You can implement whatever interface you want. A lot of times, the interface might be HTTP. In that case, you can use the Spark Job server that offers an HTTP framework, and that takes away, that way your work is limited to just having the query execution logic. This is a little bit slower, obviously, this overhead of HTTP, but still works fairly well. Another possibility is that you can use the Hive Thrift server. And let's say that you're talking about BI clients connecting via JDBC. And so you can use the Hive Thrift server and bring in the extra jars that you need. This is probably the slowest path because Hive has some overhead in terms of, for every query, it needs to look up the Hive metastore. You can get rid of most of that with caching as well, but there is some extra overhead with this method. I haven't done the analysis to understand all of it. Yeah, and thank you very much. It's an open source, probably it's an open source project, so I definitely welcome contributions. We have a mailing list, announcement list, and a Gitter channel, so feel free to look it up and come online and chat. Yeah, thanks. I'll be taking questions off. I'll be on the side taking questions. So, yeah.